Hello and welcome back to Stanton 101. This will be our video on polar coordinates, and I will recap how to convert from polar form into rectangular form, as well as how to graph polar coordinates, create equivalent coordinates, and briefly touch on polar shapes. Most of these examples will be taken from Chapter 6 in the textbook, so feel free to follow along. In polar coordinate form, the coordinates are given by the form r, theta, where r is the directed distance between a point O and any point P. In polar coordinate form, the coordinates are given by the form r, theta, where r is the directed distance between point O, which is called the pole, and any ray P. Theta is the directed angle with an initial side at the polar axis, which is here, and a terminal side at the ray determined by the set of polar coordinates, which would be here. These definitions can be found in your Precalculus textbook in section 6.4, and I will take an example from there now. Here we have a polar coordinate at 2, pi over 3. So this means that we can draw a polar axis here with point O and a line approximately 2 units at an angle of pi over 3 radians, which is about 60 degrees, so we can plot that about here. Now, there are different ways to arrive at this conclusion. Another way to determine other coordinates equivalent to the one we just graphed is to use these two formulas here. Formula 1 is r, theta plus 2n pi, and formula 2 is negative r theta plus 2n plus 1 all times pi. In this case, n can be any integer and theta is any angle. We can take the original set of coordinates we had before and use these formulas to generate equal coordinates. If we plug in 2 for r and pi over 3 for our theta, we get 2 pi over 3 plus 2n pi and negative 2 pi over 3 plus 2n plus 1 times pi. If we assume that n is 1, we can go ahead and plug in and simplify. So then we get 2 plus pi over 3. Now we have to make the 2n pi have an equivalent denominator to the pi over 3. So we're going to multiply it by 3 on the top to get 6n pi over 3. And now we can add it to get 2, 7 pi over 3. And here we have our second equation, which is going to equal negative 2, negative 4 pi over 3. And since I already showed you how to simplify it in the top equation, I'm not going to go ahead and bother with the second. This whole process is the same thing as adding 360 to the degree measure of theta, which is 60. So 7 pi over 3 is the same thing as 420 degrees, which is what you get if you convert. And the reason why negative 2, 4 pi over 3 is the same thing as the original problem is because we added the equivalent of 180 to 60 degrees, which would be a rotation, moving the ray from the first to the third quadrant. The negative in front of the 2 flips the ray back into the first quadrant and into the original position. Just like when measuring angles, there are an infinite amount of polar coordinates equal to the original, and can all be found by using the formulas we just covered. Next, I will be discussing coordinate conversions. We can take polar coordinates and turn them into rectangular coordinates by using these formulas. X equals r cosine theta and y equals r sine theta. If we want to convert, for example, 4, 7 pi over 6 to rectangular form, we would use these formulas to show that x equals 4 cosine theta and y equals 4 sine theta. By using our unit circle values for the cosine and sine of 7 pi over 6, we would know that x would equal 4 times negative root 3 over 2, and y would equal 4 times negative 1/2. If both of these values are simplified, we get approximately negative 3.46 and also negative 2 for your y-coordinate. So now we can go ahead and say that the polar form of 4 7 pi over 6 equals negative 4 root 3 over 2, comma 2, or negative 3.46, comma, negative 2. If going from rectangular form to polar form, we can use the formulas r squared equals x squared plus y squared and tangent of theta equals y over x. Using a modified example from the textbook, if we have the rectangular coordinate negative 2, 2, we can plug in both x and y into the first equation, giving us r squared equals negative 2 to the second power plus 2 also raised to the second power. Therefore, r equals root 8, which is also equal to 2 root 2. We also have to remember that this can be positive or negative since it was the square root. So now we know that r is positive or negative 2 root 2, and we just have to find theta. In this situation, tangent of theta equals y over x, which is 2 over negative 2, which equals negative 1. The inverse tangent of negative 1 is equal to theta, which equals negative pi over 4. We must consider the negative 2 root 2 for a minute. When the value of r is positive, nothing must be done to theta. However, when it is negative, the quantity pi must be added in order to keep the ray in the same position. There must be a double flip of sorts to make the values the same. Of course, there are infinite values of theta, but for our purposes, we can say that the polar coordinate form of negative 2, 2 is 2 root 2, comma, negative pi over 4, and negative 2 root 2, 3 pi over 4. You can also convert from polar form to rectangular form and vice versa when given a formula rather than a pair of coordinates. For example, we can take this equation, r equals 4 cosine theta, and multiply both sides by r to get r squared equals 4r cosine theta. The next step is to substitute r squared with x squared plus y squared, which is derived from the formula that we used earlier. And since we know that r cosine theta is also equal to x, this side can just be substituted by saying 4x. So now we have a new formula, which is x squared plus y squared equals 4x. What we have to do next is we have to get the 4x onto the side with the x squared, so we can subtract the 4x, and now we have to complete the square. So I'm going to add 4, and we're going to have to add 4 to the other side, but first we have to finish with the y squared, and then now we can add the 4, and I had it in a different color to show you that it was not part of the original equation, but since we have to complete the square, if you add 4 to both sides, it makes everything alright. So now the quantity x squared minus 4x plus 4 can be condensed and factored into x minus 2 squared, then we can add our y squared here, equals 4. So now we have the equation of a circle, which if you graph it, this would be the form of this polar equation in the Cartesian plane. It won't always be a circle though, sometimes it can be a line or some other form of graph, but in this case, it will be a circle. This formula is taken from chapter 6 in our textbook, and we're going to convert this formula into polar form. So the first thing to do is we have to expand this formula by foiling everything out and adding it all together on one side to get this long formula equals 13. Now let's rearrange it so that we have the x squared term first, followed by the y squared, plus the 6x and the 4y, or subtracting both of those, but adding them to this side of the equation. And then we have the 9 and the 4, which equals 13, so the 13's on both sides cancel out to get 0. Now what we have to do is we have to substitute r squared for x squared plus y squared, and r cosine theta for x, and r sine theta for y, which gives you r squared minus 6r cosine theta minus 4r sine theta. Oh, well, and it equals 0, so now we can factor out an r to get r minus 6 cosine theta minus 4 sine theta, equals 0. Now in this case, r can equal 0, or the equation can also be equal to r minus 6 cosine theta minus 4 sine theta equals 0, which is what we're going to go with since we're assuming that the radius is not going to be 0. So this can be simplified to r equals cosine theta plus 4 sine theta, since if we wanted to isolate r, we would have to add both cosine and sine values to the other side. Lastly, I'm not going to go super in depth about these, but they're good to mention. So these are polar forms, polar shapes, and first off we have rose curves. So the graphs of polar equations can be described by r equals a cosine n theta and r equals a sine n theta. All of this is assuming that n is an integer greater than 1. If n is an odd number, then we can assume that there will be n amount of petals. But if n is an even number, then we can assume that there will be 2n petals. This here is an approximate graph of what a rose curve might look like. And of course there's going to be a different amount of petals depending on your equation. Next we have a Lemniscate curve, and these are the two polar equations to graph this form, which is r equals a plus or minus b sine theta and r equals a plus or minus b cosine theta, obviously assuming that a and b are both greater than 0. There are 4 types of Lemniscate curves, with the first one being an inner loop Lemniscate, which looks like this, and then the second one being a cardioid, which looks like this, and then a dimpled Lemniscate, which looks like this, which is similar to the cardioid, but instead of starting at the origin, it starts halfway, a negative half. And then the last one is a convex Lemniscate, which kind of looks like a circle with a flat side. The way to determine which graph your Lemniscate curve will be is to take the quantity of a over b. So if your A over your B is less than 1, then you're going to have a limitron with an inner loop. And if your A over B is equal to 1, then you're going to have a cardioid, and you're going to have a dimpled limitron if your A over B is less than 2 but greater than 1. And if your A over B is equal to 2, then you're going to have a convex limitron. Lastly, we have a lemniscate, which is represented by these two formulas here, which are r squared equals a squared times the sine of 2 theta, and r squared equals a squared cosine 2 theta. And the graph looks like this, which it kind of looks like an infinity sign centered on the coordinate plane. So these are the 3 major different polar shapes that you may see in the pre-calculus curriculum. So this is the video on polar coordinates, and I will be putting another one out on complex numbers, followed by a video on parametrics, both building off of this one. So thank you, and I hope you enjoyed.